Okay, so let's work on this problem. This is going to be our first quasi-linear equation, or our first quasi-linear equation that isn't a linear equation. So the step one is to actually step zero is to rewrite that to rho instead of u, since I've got rho over here. Step one is to write it in standard form. It's already in the form that we like to work with. Step two, what is our Cauchy stuff? Well, we're dealing, so I didn't say it here, but I did say here, t is greater than 0, t is time. We know what rho is on the x-axis, so that's going to be our Cauchy curve. So we're going to have something like this. And I know to the left of the x-axis, there, my initial values are going to be equal to -1. And to the right, my values here are going to be equal to 1. Okay, step two is to get the characteristic equations. So here, x dot is going, or sorry, t dot is going to be 1, and t of 0 is 0. So t dot is going to be equal to, oh man, t dot is going to be equal to 1, t of 0 is 0. X dot is going to be 2z plus 1, 2z plus 1 is the thing multiplying the x derivative of rho. X of 0 is going to be x naught. Z dot is everything to the right of the equal sign, which is 0 in this case, and z of 0 is going to be equal to -1 if x naught is less than 0, and 1 if x naught is greater than 0. Okay, so let's draw these characteristics. So I'm going to work on the left part of the plane, that is when x naught is less than 0. Let's solve these equations. We're going to have t of s is equal to s. We're going to have z of s is equal to z of 0, which if x naught is negative is going to be -1. And then this gives x dot of s. This gives x dot of s is going to be equal to -1 if z is equal to -1. So x of s is going to be equal to -s plus x naught. Okay, so I'll sketch these. And again, this is supposed to be for x naught is less than 0. But I'm just going to sketch the dashed line corresponding to x naught is equal to 0. That's sort of the boundary of this part of the characteristics. And then everything else is going to be at a 45-degree angle like this. Okay. So now let's look at the right half of the plane, that is when x naught is greater than 0. If x naught is greater than 0, we're still going to have t of s is equal to s. But z of s is going to be equal to 1, and x of s then, as you can see, will be equal to 3s plus x naught. So again, I'm only supposed to draw the characteristics for x naught greater than 0, but I'm going to draw the boundary one when x naught is equal to 0. These are going to be having a slope of 1/3. Okay, and so I know that on the characteristics, I know the solution is constant on the characteristics. So I know that rho is equal to 1 over here in this orange part, and I know that -1 in the orange part. Rho is equal to -1 over there in the orange part, and rho is equal to 1 over here in the blue part. I also know this region, so this line right here is t is equal to -x. So I know that the region over here is going to be t. Oh, man. I know that the region over here is going to be t less than -x. I know over here for the blue part, rho is equal to 1. And I know over here, this line here is t is equal to x over 3. So I know this is going to be x. I keep thinking I'm changing colors. I don't know what's going on. So I know this region over here is the region x is greater than 3t. Okay, so I can kind of start my solution. I know rho of xt is going to be equal to -1. So notice that I can write this as x. I can write this as t. I can write this as x is greater than -t. This is going to be when x is greater than -t. I know that it is going to be equal to 1 when I've got x is greater than 3t. And I'm going to think for a minute about what it's going to be here. Okay, I'm going to think for a minute about what is going to be there, but the inequality, so I'll do this part in red. The inequality would be minus t less than x less than 3t. Okay, now before analyzing, before trying to figure out what's going on in this region here, so in this wedge right here, we don't have one of the sort of traditional characteristics passing through, so we have to figure out what's going on there. So before we do that, I want to sketch the solution at a few different values for t. So this will be the x, that's the rho axis. This is the x-axis, this is x, this is rho. When t is equal to 0, well, I know the solution is minus 1 to the left of the axis, and it's going to be equal to 1 to the right. It's going to be equal to 1 over here. Okay, now I want to sketch what happens maybe when t is equal to 1. So this is x, this is rho. Let's sketch what happens when t is equal to 1. Well, if I look at my piecewise solution here, when x is greater than minus t, by the way, I realized I just messed that up. So that's x is less than minus t. Sorry about that. This is x is less than minus t. It's correct up here. It's correct up here. It's just not correct there. Okay, so what happens when t is equal to 1? So what happens when t is equal to 1? Well, when t is less than minus x, I mean when x is less than minus t, well, if t is equal to 1, minus t is minus 1. This is minus 1. And so the solution is going to be minus 1 here. And then for the other part, it's going to be when x is greater than 3t. So if t is equal to 1, we'll call this 3t. That's 3 times 1. And I know the solution is going to be 1 here. And what we're going to, the solution that we're going to take, remember there's many different solutions to take in this in-between part between minus 1 and 3, or minus t and 3t. But the solution that makes the most sense physically is, or the only solution that makes any sense physically, is going to be the solution that is just the linear interpolation between these 2 points here. Okay, and let me just show you what happens when t, whoops. Let me just show you what happens. Come on. Let me just show you what happens when t is equal to 2, and we'll get an idea of what's going on. So this is going to be when t is equal to 2. This will be when t is equal to 2. Wow. Okay, so they gave me a new pen to use, but it is seeming to do weird things as well. So when t is equal to 2, I know that minus t is going to be equal to minus 2. So this is minus 2. And I know the solution will be minus 1 here. Now 3t will be equal to 6. So I'll call this one 6. And I know that the solution will be equal to 1 here. And again, it's going to be the linear interpolation between the two. And notice what's happening. The length of the red part is growing. It's getting longer and longer and longer. Okay, that's why it calls it an expansion wave. The area between these 2 parts of the solution is expanding. Okay, so one way now to write the solution would be given, given that we know the coordinates of this point are going to be x is equal to minus 1. X is equal to minus 1, or sorry. On the x-axis, this is going to be minus t. And the y-axis, this will be minus 1. And if I look at this point right here, the coordinates in the x row axis, x is going to be 3t, and rho is going to be equal to 1, we could just write the formula for the linear interpolation between those two. We know how to do that. It's just a line segment. Okay, or we could think how we were thinking before. Imagine that I have a characteristic going through, so let's come back, oh my goodness. So let's come back. Okay, so if I sort of run this, if I run this in reverse, what's happening to this diagonal red line at time t is equal to 0, it's eventually going to be like this when time t is equal to 0. And so I think of sort of all of the solutions from -1 to 1 being present there. And so the idea is I'm going to think about a characteristic that passes through the point, that passes through the origin, like this. And I want to try to figure out, given a generic point on this line here, AB, what is the solution at that point? Well, I know the slope of a characteristic. Now the writing is going very slow. The slope of a characteristic is always going to be the t dot over the x dot. So in this case, it's going to be m is equal to 1 over 2z plus 1. And if I have a line that goes through the origin and the point AB, the slope of that line is b over a. So now I can solve this for z in terms of a and b. So z then is going to be equal to a over b minus 1, and all of this multiplied by 1/2. Or I could write this as a minus b over 2b. Okay, so now my solution down here, the last part here, will be x minus t over 2t. Okay, now notice when x is equal to minus t, the orange solution and the red solution match up. In other words, when x is equal to minus t, what do you have? Well, in the red solution, it'll be minus t over 2t. That's minus 1, which is what the orange solution is. When x is equal to 3t, and the red and the blue functions are equal. The red and the blue pieces are equal, so it's going to be, again, just plug in x is equal to 3t. You have 3t minus t, that's 2t divided by 2t, which is equal to 1. And then clearly x minus t over 2t is a linear function of x. So this shows you that this is the linear interpolation between the orange part and the blue part. Okay, so that was it. Try to understand these drawings here, because I think that will help you understand why we pick the characteristics that we do, or why we do things the way we do. I think it just helps visualize things a little better.